Hello and welcome to Logic Games Step by Step. I'm Michael Deere, and in this tutorial we're going to learn the ins and outs of how to diagram logic games. So let's get started. This is a logic game, and in the last tutorial we covered the parts of a logic game, and we learned that there's a lot of information that you need to process quickly and accurately. You must identify the static variable, the dynamic variables, the type of relationship, and the players to positions. You also have to process the rules, what they mean, and how they apply to your variables. And you have to do all of this as fast as possible. This is where diagramming comes in. A diagram is just a visual representation of all the information that the logic game gives you. And diagrams are effective because they help you see all of the information that you need to have and see it at a glance. Instead of reading and rereading the setup and the rules and trying to figure out what they mean, you have in front of you all at once everything laid out, and it's in visual form. So one of the most important things that a diagram does is that it helps you to organize your information in a visually simple and complete way. Another thing that a diagram does is that it helps you to see the logical relationships between different variables through a picture of how those different variables interact. This is a powerful function of diagrams because it is precisely those logical relationships that you'll need to understand in order to make use of them in answering the questions. Representing logical relationships is something that you already do, and it comes pretty naturally for us. If we want to represent 2 plus 2 equals 4, we don't write it out. That'd be silly. And we don't need to know which two things are being added to which two other things in order to make 4 of them. It doesn't really matter if it's 2 oranges, 2 apples, or 2 kitty cats. Whatever it is, what really matters is the logical relationship. So instead of drawing things out like oranges or kitties, and instead of writing it out, we use symbols and numbers. And so instead of writing or drawing 2 kitties plus 2 kitties equals 4 kitties, we simply write 2 plus 2 equals 4. This way, we're able to see the relationship between all of the elements without being distracted by irrelevant things. Our diagrams work the same way. It doesn't matter if our static element is days of the week or hours in a day. And it doesn't matter if our dynamic element is Beth, Charlene, or Mika. What matters is how they logically relate, and that's what we show with our diagram. So instead of writing out something like Christoph finishes the race earlier than Linus, we write it like this. So that's why we diagram. And the reasons why we diagram also tell us what a good diagram should look like. So let's take a look at that now. A good diagram should always be simple. Because our goal is to see everything at a glance, we need our diagram to be as simple as possible. And what we want is a diagram that's clean, organized, and immediately understandable. And another benefit of making our diagram simple is that it's quick and it's easy to set up. And that's a plus when we factor in the limited amount of time that we're going to have to complete a problem. The simpler our diagram, the faster we can set it up. The second thing necessary for a good diagram is that it is complete. We want our diagram to visually represent every single piece of information presented on our stimulus. Once we have our diagram together, we should never have to reread any of the rules or any part of the setup. We should be able to look at our diagram and trust that everything we need to know is visually represented. Third, our diagram needs to be accurate. And this seems obvious, but it's harder to do than you might think. We need to be cautious, we need to read carefully, and so we need to have an even more careful diagram in order to be accurate. So make sure that your diagram presents all and only the information given in the stimulus. And finally, our diagram has to be consistent. Every symbol that we use should be used for one and only one function. If we use an arrow to express a conditional, then that arrow needs to always be used to express a conditional and nothing else. If we use a V to represent either or, then it should always be used for that and nothing else. Never use symbols in different ways in different diagrams. Okay, so those are the parts of a good diagram. Now let's put them into practice and look at some logic games. And I'm going to walk you through some simple diagrams, and then we're going to take a look at a more complicated example. So let's get started. This is game number 1. Now, we know every game will have a static variable and a set of dynamic variables. The static variable never changes, and it's what we use to organize everything else. It's the base unit of our diagram. So what's our static variable here? Well, it's the first thing we're told. A period of 6 hours from 1 p.m. to 6 p.m. with the last session beginning at 6 p.m. Now when we diagram our static variable, we will always diagram it the same way. We will use
the power of the dash.
So 6 little dashes, and we number them 1 through 6. This little dash will be the most powerful diagramming tool in your arsenal, and we're going to use it for every static variable all the time. It's versatile, it's simple, and most of all, it's fast, and we like fast. So embrace the power of the dash. Okay, so we have our static variable, and here we have our dynamic variables, and these are like our game pieces, and we find those right here. They're generally in alphabetical order and grouped together, and these we convert to letters, and we write them out above, just like that. And now we number them. We always number them. Why? Because it's a simple way to prevent a stupid mistake. This little number prevents me from forgetting a letter or adding too many, and it helps me be sure that I have exactly the variables I'm supposed to have. Too often, I make dumb mistakes, and I might say, well, I was a dumb mistake. I know better than to do that. Well, yeah, of course I know better, but I still have to find a way to prevent those dumb mistakes. Dumb mistakes lead to points lost on the LSAT, and points lost on the LSAT leads to less scholarship money. So every time you don't write the number of variables and verify it, just go ahead, take $1 out of your pocket, or make it 10 because law school is expensive, and just set it on fire. It'll have about the same effect. So all right, we have our dashes, we have our variables. What are we being asked to do? It's pretty clear that this is an ordering game rather than an assignment game. And this means that I'm ordering the subjects studied by the hour of the day in which they're studied. Great. And so finally, what's our ratio of players to positions? Let's see. We have 6 hours, 6 subjects, 1 subject per hour. Only 1 subject is studied in a given hour. We have an equal number of pieces to spaces, so no surprises. Now let's move on to the rules. Our first rule names a static condition, meaning it fixes the position of a certain variable. And it tells us that one of our subjects must be studied, either at 1 p.m. or 6 p.m. And this leads us to an important tip. If you can put the rule in your diagram, then you must put the rule in your diagram. So we're going to put an F here and an F here, and we'll use a slash to show that it could be one or the other. You could also use parentheses or half parentheses or whatever's easiest for you, so long as you know that it means either or. Our next rule is pretty straightforward as well. One of our subjects is studied earlier than another subject. And to represent earlier and later relationships, we're just going to use a raised line like this. Now remember, the raised line is what we will always use from this day until our last day to represent earlier and later. Now we come to an interesting rule. I is studied not just before, but immediately before L. Now in our previous rule, the raised line just means that something is earlier than something else. It doesn't specify how early. It could be right before, but it doesn't have to be. So if we used our trusty raised line, we're going to get confused pretty quickly. What we want to show is not that I is sometime before L, but that I is immediately before L. So we need a different symbol. Now the easiest thing to do would be to write them together like this. But I also want to show that they're a block. They're a single unit. And so wherever I have L right after, and wherever I have L, then I know that I is immediately before. And I want to be able to reflect that visually. So I'm just going to add a line underneath. You can add whatever feels intuitive. You can use a box, or you can use a double line, or whatever you want, as long as you're consistent in the use. Now we come to our last rule, which is stated as a conditional. And we already know that we can't use the raised line because that means earlier and later. So to represent a conditional, let's just use an arrow. And the arrow will mean now and forever, if then. But what about the fact that G is third and Q is fifth? How do we draw that? How do we present a visual representation for that? Well, we're just going to use subscripts and superscripts. So we're going to write it like this. And now this is the place then for another tip. Always take the contrapositive of a conditional immediately. Do not treat it like an inference. Treat it like another rule. Any rule that gives you a conditional has effectively given you 2 rules, the original conditional and the contrapositive. Sure, it means the same thing logically, but you need to treat it like 2 separate rules. You get a conditional, immediately take the contrapositive and record it under the conditional. Finally, we want to make sure that we note any variable not restricted by a rule, and in this case that would be H. So we write out H with our other rules, and we make some notation that tells us that H is unrestricted. In other words, that H is not bounded by some rule. And I'm just going to use a drawn out U shape. Visually, for me, it means that it's like held close. And it also has the benefit of looking like a U to represent unrestricted for me. But you could also use an asterisk or a double underline or whatever you want. But again, it has to be consistent. And that's it. That's our first diagram. It's easy, it's simple, and it represents all of the information that we need. It's fast, flexible. So now let's make it a little bit harder. For this logic game, I've chosen an assignment game. And I've chosen it because it offers some interesting challenges. The first challenge has to do with the variables. Here, they're divided into categories, cellist and violinist. And the variables are not just all of one type, but they're divided between these two different types. And we're going to have to find some way to diagram that visually. The second challenge has to do with the fact that one of our positions on the board is singled out, the leader of the quartet on a given day. So each quartet's going to have a leader, and we have to find a way to visually keep track of that position and which variable occupies that position. And our final challenge concerns restrictions on this privileged leader spot. So before we even move to the rules, we have to not only account visually for the leader role, but we have to keep track of restrictions on that role and diagram them appropriately. So it's an interesting game, and it's going to test our lexicon and our creativity as we devise a simple, complete, and consistent diagram that presents the information we need to have. So let's start with the setup, our static variable. Here, it's the quartet each day over 2 days. So we utilize, once again,
the power of the dash.
And we draw 2 sets of 4 dashes to represent the 2 quartets, with 4 seats each. And to designate the quartet for any given day, we just write 1 and 2 under each of our 2 sets of seats. Now for each day, we have a full quartet, and we have 4 seats per quartet, and that gives us a total of 8 seats. Now let's turn to our dynamic variables. Our dynamic variables are divided into 2 categories, cellist and violinist. And believe me, it does matter who's who. So right away, we know that we cannot simply write out our variables like this, ignoring who's a cellist and who's a violinist. That won't help us at all. We have to be able to tell the difference. I suppose if we wanted, we could write out each category. We could write out cellist and then write out violinist, and we could put the variables that apply to each category next to them. But that took a long time to write out, and we don't want to waste that kind of time if we don't have to. So let's go ahead and get rid of that and find something simpler. Instead of writing out our categories, let's just give them letters. And in order to be sure that we don't think of them as variables, let's just go ahead and circle them. So we'd write it like this. Now, remember, we have to be consistent. So from today until the end of days, a circled letter is always going to mean a category and not a variable. It will convey a type. So here, the circled C will mean the category cellist, and the circle V will mean the category violinist. And I circle these once again so that I don't think that they're variables. All right, so that's challenge number 1 out of the way. But connected to this is another challenge. Only some of each category are used. Specifically, our stimulus tells us that 2 of the 4 cellists and 2 of the 3 violinists are going to be in any given quartet, and we need to be able to represent that. So how do I show that only 2 are used in each case and in each quartet? Well, the answer is pretty simple. Next to my categories and variables, I'm going to write 2 out of 4 next to cellists and 2 out of 3 next to violinists. And this tells me that 2 of the 4 cellists will be in the quartet and 2 of the 3 violinists will be in the quartet. Now, if it helps, I suppose I could write quartet or per quartet or, circle over these numbers to tell you the number per quartet. But I think it's pretty clear as it stands. Now let's deal with the third challenge. One of our positions in each quartet is privileged. There's a leader in each quartet. So how do we meet this challenge? How do we visually record that one of our positions is the leader? Answer, keep it simple. Let's just pick one of these dashes and we'll put an L next to it. And we're going to circle that. And this just means that whatever variable is in this area is our leader. But we can't just leave it as a letter, so we have to circle it so we know it's not a variable. And now we know that in this position, that's going to mark out our leader position. So whichever variable is there, that's going to be the leader in the quartet for that day. And the last thing we have is restrictions on that leader position. And they're restrictions that look like they might be tough to diagram. But not for us, right? Because we're diagramming masters. So we're going to keep things simple and we're going to keep things clear. So let's go ahead and give a visual picture. The first restriction says that the leader on the first day cannot be in the quartet on the second day. So we're going to borrow our use of subscripts from the previous diagram and use those here. And we're going to write L1 to indicate the leader in the first quartet. And we're going to go ahead and write it out with an equal sign. And then let's use a crossed out 2 to indicate that the leader on day 1 is not in the quartet on day 2. so that now this says whoever's the leader in the first quartet cannot even be in the second quartet. You could also represent this as a conditional, but personally I think that's overcomplicated. This says everything we need it to say. Now to the second restriction, and this restriction says the leader on the second day must have played in the quartet on the first day. So again, we're going to use the subscript and equal sign, and we'll write it out like this. And what this says is that the leader for the quartet on the second day had to play in the quartet on the first day. And now we can also put this in our master diagram as well, so that it looks like this. Because if we can put it in our master diagram, then we must put it in our master diagram. And that's it. We've tackled all of the major diagramming challenges for this game, and we can move on to the rules, which turn out to be relatively straightforward. But these rules do present an opportunity for offering another tip. Always diagram your rules as they will appear on your board. Why? Because that's the whole point of diagramming. Remember that an important part of your diagramming is to visually represent logical relationships so that you can see them more clearly. But if you don't diagram your rules the way they will appear on your board, that doesn't really help you to see those relationships. It doesn't help you to visualize the impact of the rule or to see what it means for your setup. So you're not diagramming just because that's what you're supposed to do on the LSAT. And you're not diagramming because everyone tells you to diagram or because your prep book tells you to diagram. You're diagramming because it's the fastest, easiest way to see the logical relationships that you need to understand to solve the game. And if your diagram doesn't help you do that, then your diagram's useless. So our first rule says, N and W do not perform in the same quartet on the same day. And we diagram it this way because it looks like it would in our diagram, with one variable on top of another. And we put a box around it to indicate that we're talking about the same quartet. And we put a line through it to show that these two will not be in the same quartet on the same day. And our second rule says the same thing about O and Y, so we go ahead and diagram that this way, and we do so for the same reasons. Now our final rule presents our final challenge. So let's take a closer look at this rule. It says that on each day, either P or W, but not both, performs in the quartet. And that's a little bit tricky. How do we keep this rule simple, but also keep it visually accurate? And so maybe we'll do it something like this. And this says that on both days, either P or W plays, but not both. But I really don't like the look of that. It's clear enough, but it's hard to visualize that in relation to my diagram. And for me, I think I might get misled pretty easily by that. And even though it's accurate, for me it's confusing. So let's try a few different ways. I could visualize each quartet, and I could just put P-W to represent either one or the other on both days. That's another way. Or finally, I could break out trusty old equal sign, and I could write it like this. The first and third way, I just find confusing. And remember our tip. Try to draw out the rule in a way that matches how it will appear in your diagram. So I'm going to go with the second version that looks like this. So that's the one I'm going to put in our game diagram. Now, why am I not putting this in our master diagram? Because I don't know if one of them will or will not be the leader. And if I draw it in my diagram, I don't want to put it in the leader spot, because that seems to imply that either one or the other will be the leader. But I also don't want to leave it out of the leader spot, because then that indicates that maybe neither of them is the leader. They're always not the leader of the quartet. So I'm going to draw out the rule here to the side, but I do it as it will probably appear in my actual diagram. Now, in effect, this one rule gives me two rules, and I don't see any reason why I shouldn't represent it as two separate rules. Because again, I'm interested in the logical relationship that it expresses. And so if that's easier to express as two rules, then I might as well do it that way. And the first rule is what we've already diagrammed. In any quartet, either P or W is going to be a member, and so that's already recorded. But it also says that they will not play together in the same quartet on any given day. So I can have one or the other, but I can't have both. And that means that this rule is exactly like my other rules. And so I'm just going to write it up here next to them for the sake of simplicity, and I'll record it in the same way that P and W can't play in the same quartet on the same day. And there we go. That's our second diagram. Not much harder than the first, but different. So now let's turn to our final game. And here it is. Just like the previous game, it poses a few challenges that I think are helpful for rounding out our understanding of diagramming. And then after this game, we're going to take stock of what we've learned. This is another ordering game. And once again, we utilize the power of the dash. Our static variable is the rooms in the hall adjacent to each other, numbered 1 through 9. And like all ordering games, the numerical sequence is our clue for finding that static variable. This is the variable that will never change, and so we just put down 9 dashes and we number them 1 through 9. Easy as pie. Our dynamic variables are these right here, B, C, D, E, and F. And we write these out over to the side. And of course, we also know now that we number them. There are 5 variables, so we write 5 next to it and we circle it. The next thing to look at is our players to positions. And we see that we have 5 housekeepers, but we have 9 rooms. So we know that at least some of the housekeepers are cleaning more than one room. But there's a restriction. And that restriction says each room is cleaned by exactly one housekeeper and no housekeeper cleans more than 2 rooms. Okay, so what do we do with this restriction? How do we visually represent that no housekeeper cleans more than 2 rooms? And how do we determine who's cleaning extra rooms? Well, let's take a closer look at this condition. Essentially, it means that every housekeeper but one has to clean 2 rooms. 5 housekeepers, 9 rooms. If everybody cleaned a room, that would be 10 rooms, one more than we have. So 4 of them clean 2 rooms and 1 of them cleans 1 room. So what we really need to know then is who is it that's only cleaning 1 room? Do we have any idea who's cleaning just 1 room? And as it turns out, we do know that. Our very first rule tells us that. Fiona cleans only 1 room, so she's the singleton. So now we have everything we need to diagram this restriction simply. If F is the singleton, then everyone else cleans 2 rooms. So instead of writing out a rule that says each person cleans at most 2 rooms, but not none, we can make it simpler than that and just write every variable twice except for F. And it looks like this. Now we have all of our actual variables, and they're laid out visually in front of us according to how they're going to be used in the game. But you might be saying to yourself at this point, wait a minute, that's wrong. No housekeeper can clean more than 2 rooms, but it doesn't say that a housekeeper has to clean a room. Maybe there's one housekeeper who doesn't clean any of the rooms. And so recording the restriction the way I have here is inaccurate because it assumes that all the housekeepers will clean a room, and the stimulus doesn't say that. Fair enough, but this can't be true, because if one housekeeper cleans no rooms, for instance, then we basically have 4 housekeepers, not 5, and one of them still only cleans 1 room. So if no housekeeper cleans more than 2, and we have only 4 housekeepers and one of them cleans only 1 room, then we'd be able to clean 7 rooms, but we wouldn't be able to clean all 9, because 3 of the housekeepers would clean 2 rooms and 1 of the housekeepers would clean 1. So even though technically the rule doesn't state that a housekeeper must clean a room, the layout of the game demands it. It's the only way to have enough housekeepers to clean each room if no housekeeper can clean more than 2. And so that means that our way of recording this rule is accurate. We simply write every variable twice except for F. All right, so this leads us to another important tip. Diagram the meaning of a rule, not the wording of the rule. Never let the LSAT dictate how you represent a rule, because a lot of times the LSAT's going to present that rule in a confusing way, and it does this specifically to throw you off. When a rule's presented in a confusing way, there is always a simpler way to record that rule, and you can find that simpler way by focusing on the meaning of the rule rather than what the rule says, right? But it's still up to you to find that. Let's take a look at an example before we move on. Suppose that a rule said the following: A comes neither immediately before nor immediately after B. And if we diagram this rule according to the language of the rule, we might write it this way. And really, most of my students initially, they diagram the rule this way. But that's not what the rule means. What the rule means is that A and B never occur consecutively. They're never next to one another. And the simplest way that we diagram that rule is this way. Now, here, I don't use a box or a line. I'm using a circle to indicate that A might come before B or that B might come before A, because I don't know which one's first. I just know that they're not next to one another. And the line that I put through it says they're never next to each other. So what this says is A and B are not consecutive, that A and B never occur next to one another regardless of who comes first. The same rule, the exact same rule, could be worded this way, there is at least one space between A and B. And again, most of my students would diagram that rule this way, at least at first. But of course, that's not what the rule really means. Just as before, the rule means that A and B are not consecutive, and that's the way we draw it. It's the same exact rule, but depending on the way it's presented, it can look very, very confusing. So the way to simplify a rule is to always diagram what the rule means logically, not just what it says. Because a lot of times the rule's going to mean something simple logically that's being presented in a confusing way. Okay, so let's go back to our game. We have our static variable, our dynamic variables, our players to positions, and we know we're ordering our variables 1 through 9. Now let's diagram the rules. The first rule we've already dealt with, and it gave us our total variables. The second rule is a nice, juicy static rule. We love static rules, and it tells us that C is always second. And now we know that if we can put it in our master diagram, we must put it in our master diagram. So let's go ahead and add that right on in. Our next rule is another static rule filled with juicy goodness. Awesome. So let's go ahead and put that in our master diagram as well. Underneath the first position, we'll just write the letter E, we'll cross it out. So far, so good. Now we get a rule about consecutives. Beth doesn't clean consecutive rooms. Well, we've already covered this indirectly. So we're going to write both B's next to each other, draw a line under it, or a box or whatever, and negate it, just like that. Beth doesn't clean consecutive rooms. Now we have that represented. And now we get to our first really interesting rule. And this rule is a lot easier than it looks. It tells us that there's exactly one room between the rooms that Emma cleans, and that room is being cleaned by Charlie. So we can just draw it out like this. And because this is how it will appear in our diagram, it's very, very clear what the rule means. And we just draw a line beneath it to tell us that it's a block. These three go together. Now the next rule could present some trouble. Not really for diagramming, but for diagramming correctly and accurately, because this rule actually conveys quite a bit of information. It tells us that one of David's rooms is an end room, so it's either 1 or 9, but it also tells us only one of the rooms that David cleans is an end room. The other room he cleans must not be an end room, but it can be any other room in between. In other words, for one of David's rooms, it's an end room, for the other, it's not. I'm a big believer in that initial tip. If we can put it in our diagram, we must put it in our diagram. So I'm going to go ahead and do that right here. And this says that one of the rooms that David cleans is either 1 or 9. But now we have to do that other bit about the room that he cleans that's neither 1 nor 9. And what do we do about that? We could record it separately this way. And this says that D is not both 1 and 9. But it's a bit confusing since it forces me to remember that even though D is not 1 and 9 together, it's still at least 1 or 9. And so I think personally it just adds a bit of confusion. We could write it as a conditional, and that would mean that if D is in the first position, then it's not in the 9th. And by the logic of the conditional, if D is in the 9th position, then it's not in the first. And this would also mean that D can't be 1 and 9, since the antecedents of a conditional and its contrapositive can't be true together. The problem, though, is that the consequence of a conditional and its contrapositive can be true together. And so by the logic of a conditional, it could be true that D is neither 1 nor 9 for either of its rooms, and that would violate the rule that we're given. My advice is avoid this kind of confusion altogether and just leave it as I have it in the diagram as an either or. And if it makes you happy, you can just write a subscript for D to indicate that it's only one of the rooms that he cleans and not both. And this now says that D's first room is either 1 or 9, and it says nothing at all about the second room. And if it makes you even more at ease, you can write beneath that D's second room is neither 1 nor 9. And this would help you to be sure that David cannot have both rooms at both ends. Now we get to our final rule, and this one is pretty tricky. It's a good challenge. And it says that the room that Fiona cleans is numbered higher than either of Charlie's rooms, but lower than at least one of David's rooms. Now, we've seen how to diagram higher and lower, like earlier and later. So if that were all there was to this, we would simply write it out this way. But there's that pesky at least. F is higher than either of C, but it's lower than at least one of D. At least one of. That's the tough part. If I just use the raised line, it's not going to convey the rule accurately, because it would just say that F is earlier than D, but it doesn't tell us whether it's earlier than one or both rooms or what. And really, it doesn't have to be earlier than both. It could be later than one and earlier than another. And so we have to find some way to handle all of that apparent ambiguity. So let's take a moment and look at how we might diagram things like at least and at most. The first thing to remember is that we want to be consistent. Whatever we choose, we want it to always be used that way. And so we can't just recycle symbols from our lexicon. We've got to be creative. We don't need a perfect diagram solution. We just need it to be visually obvious as to what it means. And of course, we need it to be simple and accurate. So how do we do that? Well, this is my solution, but your own can be different. Let's suppose that we want to say at least one, as in there is at least one space between A and B. We know that at least one means one is the minimum, but there's no maximum. In other words, one is the bottom value. It's the least amount of spaces that could be between A and B. So I'm going to represent that with a downward arrow pointing to the floor, and I'll represent the floor with a line, and then I'll put a 1 next to it. What this tells me visually is that the 1 is the floor number, the bottom value. So when I see an arrow pointing down to a dash on the floor followed by a number, I read that as at least that number. So here, at least 1 is written the way I have it. And the downward arrow pointing to the floor is my visual clue that it's a minimum value. It's an at least. But I also now have a strong convention for representing at most, and I can simply reverse the arrow and point it at the ceiling. So suppose I wanted to say at most 2, then I would write it like this. And the upward arrow pointing at the ceiling reminds me visually that I'm dealing with a maximum value and not a minimum value. Now, I like this because I like pictures. I like the visual designation that tells me in a picture, so to speak, what exactly is going on. But many of my students prefer something like this, and they use the at symbol and a lowercase l for at least, and the at symbol and a lowercase m for at most, and they write it the way I've written it here. Do whatever works for you, but remember to make it simple, make it consistent, and be sure that it's accurate. So now let's go over and put that into our diagram. And so our final diagram for the rule would look like this. And the at least is represented between Fiona and David to show that Fiona cleans a room before at least one of David's rooms. And that's it. We're done. We've now done 3 different games. And so let's take stock for a minute about what we've learned. The first thing we've learned is to diagram the information, not the game type. The purpose of the diagram is that visual representation of information, and the goal is to be able to see logical relationships. But too many people think that they're diagramming a game type, a linear game or a grouping game or some other kind of type of game. But I think that that approach is too restrictive. And I've noticed that there have been logic games that seem to defy easy diagramming and don't really fall into the categories that, many students use to diagram. And so I think the best way to think about a diagram is that you're diagramming the information in the logic game. You're not diagramming a type of game. And if you think in terms of information, it will tell you a lot about how to diagram, because the information you need to represent is going to control the kind of diagram that you produce. But if you're focused on the game type and diagramming it appropriate to the game type, you might miss some important pieces of information that should be driving how you visually represent your diagram. The second thing we learned is that you should be using the diagram to help you see logical relationships. Diagram your rules the way you expect them to appear in your diagram. So if you can put a rule in your master diagram, you must put the rule in your master diagram. And you want to represent that rule in a way that allows you to visually examine the relationship expressed by the rule. And if the diagram doesn't help you be clear about those logical relationships, it's not a good diagram. The third thing is follow what works for you. I've used in this tutorial my lexicon, but you can use whatever works for you. Just remember that it must be consistent. Never change what your symbols mean. Not ever. And that way, you'll always know at a glance what your diagram means for every game. The fourth takeaway is that you should always be practicing your diagrams and improving your lexicon. And this is more a study tip as you work on logic games. When you complete a game and you've answered all the questions, save your diagram. Go back later or after you've completed the game and ask yourself, did your diagram help you or hurt you? Can it be improved? Is there an easier way, a simpler way to represent the information that you now know you need? Did you miss information? And whenever you encounter new rules, find some consistent way to diagram that rule and add it to your lexicon. If you've never seen at least before, then come up with a way to diagram that kind of rule, because you will see it again. So put it in your lexicon to remember for next time. Now finally, I'll give you my 2 cents based on my experience as a tutor. Many times when students come to me about logic games, they complain that they just keep missing inferences. They don't see the inferences that they feel like they're supposed to see in order to answer the questions on the logic game. But when we actually drill down and work a logic game together, the problem's not about finding inferences, it's about their diagram. And that makes sense to me, because if your diagram is poorly constructed, if it's badly laid out or messy, then it's going to actually prevent you from finding inferences. The cleaner your diagram, the better that diagram represents the logical relationships, the easier it is to be able to find those connections and inferences that you need to solve the game. All right. So my 2 cents about this is it's really never a question of inferences. It's a question of your diagram. And if you want to correct or improve the ways that you find inferences in a logic game, improve your diagram. But if you feel like your diagram is pretty good, but you're still not finding inferences, then take a look at my other tutorial about how to find inferences in logic games. Maybe you'll find something there that helps you to improve your ability to draw inferences. Thanks for watching and good luck with your prep.